Hi everyone, we're talking about sequences today. And a sequence is just a list of numbers, okay? So you'll see it given as a function, and as you input positive integers into your function, it'll give you a list of numbers like so, like in these examples here. So a little bit of review. An arithmetic sequence is one where the common difference can be found by subtraction, okay? So each time you're adding on a common difference. Okay, and so you can find the nth term of an arithmetic sequence, which we'll call a sub n. Remember, this is just a naming situation here. N just tells us which term we're dealing with here. Okay, so if I want to find the nth term, then I have to start with the first term plus n minus 1 times d, where d is my common difference. And you find d just by subtracting like your first and second terms. So in this case, my d would be 8 minus 3, which is 5, or 13 minus 8, which is 5. It should always be the same. A geometric sequence is similar, except instead of adding a common difference, you're multiplying a common ratio. And so the nth term of a geometric sequence is going to be your first term times your common ratio to the n minus 1 power. Okay, and the way that you find your common ratio is you just divide two of your terms. Okay, so in this case, if I divided negative 15 by 5, I would get negative 3. That would be my common ratio. Or if I divided 45 by negative 15, I also get negative 3, or so on. You should always be able to divide any two subsequent numbers. I don't know if I used the right word, but whatever. Okay, and then we have some sequences that are neither here nor there. Okay, like so, like n squared, 3 to the n plus 1, and then these rational functions here. Okay, so the way that we can tell if a sequence converges is we can take the limit to infinity. Okay, and so if we get an answer, then essentially it will converge. So let's test this out. Right, so right here, this is called my general term. I'm going to evaluate the limit as, all right, don't know what happened. The limit as n approaches infinity of 1/2 to the n minus 1 power. Okay, well, this is the same thing as 1 over 2 to the n minus 1 power, and if you plug a real big number in for n, this will tend towards 0 because it's 1 divided by a very large number. So this will approach 0, which means that this does converge. Okay, it converges to 0. Right, same deal here. So if I evaluate the limit as n approaches infinity of my general term, it's actually pretty much the exact same problem as up here. Hey, this will also tend towards 0, and so I can say that it converges to 0. Okay, and using these two examples, I can kind of come up with a general statement. And so we'll just run through this one again. If I evaluate the limit as n approaches infinity of 3/5, you will get that this tends towards 0 as well, and this converges. And so I'm going to come up with a general statement by saying that if my common ratio is less than 1, so the absolute value of my common ratio is less than 1, then my geometric sequence will converge. Okay, now it won't always converge to 0, but it will converge. Okay, now if I have a common ratio greater than 1, you can probably guess what happens. It's going to diverge. Okay, and if you just think about what you're doing, you're multiplying your ratio to each successive term, and so it'll just keep getting bigger and bigger and bigger. If your ratio is greater than 1, it'll keep growing, and so it'll never converge to a point. The values will never decrease. They'll keep increasing for forever to infinity. Okay. All right, let's do a couple more examples. So here we have sine. So if, again, I'm going to evaluate the limit as n approaches infinity of my function. Now the problem with sine is that it oscillates. Okay, you know what the graph looks like. It goes like this in both directions. Okay, and I want to know what's happening as I approach infinity. Well, you kind of oscillate between, the range of sine is -1 to 1, so you just oscillate between these values. Okay, well, basically the definition of divergence is that it does not converge. Okay, so if your limit does not converge to a single number, which this one does not, okay, it keeps rotating between these numbers, it's cyclical. Okay, so if it does not converge to a number, then it is divergent. So this is divergent. The reason why it diverges is because it oscillates. Okay, so anything that oscillates, okay, it never converges to a single number, then we will call that divergent. Okay, now here you can probably see what it'll converge to already, but again, if we evaluate the limit to infinity of my function, okay, I'll just write a to the n. Okay, remember, if your powers are the same, you just compare their leading coefficients. So the answer to this limit would be 3/5, which means that it does converge. It converges to 3/5. All right, this is another one where it oscillates. Now, if you can imagine, like if you plug any odd number in, okay, you'll end up getting a value of 2. If you plug any even number in, you'll end up getting a value of 4. And it'll just keep going between these. Hey, it never converges to a number, and so if it doesn't converge, then it diverges. I'll say it's divergent because it oscillates. Okay, last one. No, sorry, not last one. Last one here. I'm going to take the limit as n approaches infinity of natural log of n divided by n. And now, if you plug infinity in here, you get indeterminate form. You get infinity over infinity. And so I know that I can use L'Hopital's rule. So I'm going to take the derivative of my top and bottom. The derivative of natural log of n is 1 over n. The derivative of n is 1. So now if I evaluate the limit of just 1 over n, I get that it approaches 0. And so this is convergent. All right, and now last one. Okay, let's deal with factorial. All right, so the way that we're going to deal with our factorial is because these have a different constant on the inside, I'm going to write this out. So I have the limit as n approaches infinity, n plus 1 factorial over n plus 3 factorial. Now the way that factorial works is you decrease a number each time. So n plus 3 factorial is n plus 3 times n plus 2 times n plus 1 times n minus 1. Well, from this step, I can just say that it's n plus 1 factorial. So you can kind of decompose it in this way, right? Just by decreasing what's in your parentheses by 1 each time. And what happens is, now my n plus 1 factorial cancels with my n plus 1 factorial. I end up with just the limit as n approaches infinity of 1 over n plus 3 times n plus 2. And now I see that this will tend towards 0 because I have a polynomial on the bottom and a constant on the top. Okay, so again, this one is convergent. All right, and that's it. I'll see y'all later.